those that are signed up. Instead, if you have any questions, please put them in the chat or the Q&A, and we'll give it maybe like another minute. And then when you want to get started, David, go ahead and introduce yourself.
Thank you very much. Just 4 seconds here. Get everything ready to go? All right, well, I'll go ahead and get started. My name is Dave Phelps, Dave. I don't care what you call me, it's fine. I am a geotechnical engineer. I've worked for a company called GeoEngineers for the last 24 years. I have 27 years of experience. For you students out there, I didn't get my engineering degree till I was almost 30. I started off, I graduated high school, and I worked in construction, did a lot of things. But I decided I wanted to get an engineering degree, and I was fortunate. I went back to community college and learned a lot of things that I needed to learn. And then I live in California, and I went to San Francisco State and got my degree in civil engineering. But my specialty is geotechnical. So I design foundations, earthwork, anything related to foundations, retaining walls, do a lot of seismic analysis because that's a big part of foundation design. And we'll see some of that in this presentation. I'm going to be talking to you about the Puget Sound Energy Tacoma LNG facility. I'm going to have a little PowerPoint presentation here that let me launch that and share it with everybody. Let's get the right button here. Screen. Share. Watch this. From the beginning. There we go. All right, hopefully you can see my screen. Megan, let me know if there's a problem. So, like I said, this is presentation focuses on the Puget Sound Energy Tacoma LNG facility and providing clean energy. LNG, slide here. So a little bit about the utility that built this project. Tacoma, PSE, Puget Sound Energy, I'm sorry, is the largest commercial energy supplier in Washington State. They provide natural gas and electricity to over 1 million customers. They serve a large portion of Washington State. They're a pretty substantial company. They have significant assets. And they've been a client of GeoEngineers for a lot of years. We do a lot of interesting things with them. This project was one that I got to work on. And what we did here was build a facility to take natural gas and liquefy it. So the natural gas is the same gas that heats people's homes, that's in the pipes that come to your house if you have gas, and you use it for heating, hot water, cooking, etc. What the LNG facility does is it gives PSE the ability to store a lot of natural gas in a liquid form. As you can see from the slide here, you can reduce the volume of the natural gas by 600 times by chilling it to pretty significant minus 260 degrees Fahrenheit. And that way it can be stored and kept in a special tank that is part of this project. And it's not under pressure, it's actually super chilled, and it's just contained in a giant thermos bottle, an 8 million gallon thermos bottle. The purpose of the LNG facility is, like I said, to allow PSE to provide its customers with natural gas during periods of high demand. And we'll talk about that a little bit. It's called peak shaving. When we have cold weather, periods of extremely cold weather, gas demand naturally goes up because people are using it for heating, and Puget Sound Energy has to have the ability to provide that gas. So that's one of the primary goals. The other one is to provide LNG, liquid natural gas, to transportation companies, like shipping companies like Tote Marine, and for trucks and ferries and other large vessels that can be converted over to LNG because it's a cleaner fuel. So some of the potential applications, Washington State Ferries has looked at it. I don't know that they'll convert over anytime soon, but probably in the future. Tote Marine, the big shipping company here in Tacoma that carries goods to Alaska, has converted their ships over, and that was one of the primary drivers for designing and building this facility. A little bit about peak shaving. The graph just kind of shows the demand that Puget Sound Energy has for gas in certain times of the year, and you can see that November, December, January, when we have our cold months here, that there's a high demand, and so this facility allows the liquefied LNG to be regasified and injected into the system to provide people a constant and steady when it's in high demand. For PSE, one of the economic drivers is to be able to balance the use of the gas. So they look very carefully at when they would need the fuel for transportation, which is pretty much constant, but also when they would need it for peak shaving, which can vary. So they spent a lot of time doing the economic research to make sure that the economies of scale, if you will, were made sense economically before they moved forward with developing and designing and building this facility. Natural gas has some very significant environmental benefits. It's still a fossil fuel. It's not a renewable resource, but it is a much cleaner and more environmentally friendly resource that could be used to move significant quantities of goods. And because the environmental agencies have increased the requirements for reducing greenhouse gases and reducing particulate matter emissions, LNG is something that makes a lot of sense. Just a graphic that helps explain the difference between the quantity of carbon dioxide that's emitted per kilowatt hour of energy developed, and natural gas is at the top of the graph. Gasoline you see there, diesel is a little further down. This is just the carbon dioxide emissions that are reduced by using natural gas. It doesn't really address the particulate matter, and we'll talk about that a bit too. I know this is a boring slide with a lot of words, but I just wanted to point out as we move forward here that the design of this facility is very regulatory driven. There are some very stringent codes for designing an LNG facility. There are fire codes, there are vapor dispersion codes. Those are all things that are very important to the safety and the design of the facility. For me, as a geotechnical engineer, in my team, we focus mostly on the seismic design criteria, and they are delineated by code to be very stringent. The safe shutdown earthquake, for example, for an LNG facility has a recurrence interval of 2,475 years, which is significantly a much more significant event than, say, your transportation departments would apply to even roads and bridges. So kind of the bottom line here is that, and we had these discussions with people when we were trying to move this design forward, is that this facility is a very safe facility. It's designed to be safe. It's designed to survive a major earthquake to standards that are much higher than a lot of other things, including a lot of buildings and other infrastructure, including highway bridges. So the bottom line for LNG and its benefits are that it's safe. The facility is designed to be very safe. It provides heat and gas during periods of high demand for Puget Sound Energy's customers and in the area where I live. And LNG is an environmentally responsible transportation fuel that is being taken advantage of. So a little bit about the project. We're here. I don't know where folks are from, but I live just outside of Tacoma, Washington, south of Seattle, in the Puget Sound area. It's a beautiful area. We have incredible waterways, and the onus for this project was to provide gas for shipping. Ships that move goods up and down the coast, particularly from Tacoma up to Alaska. Most of the goods that you buy in grocery stores in Alaska are actually shipped from the Tacoma area. So here's a little bit of a close-up. The facility is actually located within the port of Tacoma. They're a a major port, major West Coast port. You could see the kind of the developed area there. The facilities on the peninsula between the two main waterways. Zoom in on that a little bit. This slide is from one of the reports that we generated. The site itself was it's about 30 acres. It's a site that's historically been used for industrial purposes. It had a number of warehouse buildings and other infrastructure that was taken down to make room for the new LNG facility located between those two waterways, the Blair Waterway and the Hylabos. So next slide. I realize that this is a little cluttered and maybe kind of difficult to follow, but again, these are the plans that we generated to superimpose the footprint of the facility onto all of the subsurface explorations that were completed to develop an understanding of the subsurface conditions at the site, which is a basis for designing a foundation for a facility like this. Again, cluttered and maybe difficult to understand or see, but this is just a sample of one of the many cross sections that were developed. We completed explorations where we drilled holes, took samples, or we pushed instruments into the ground to develop a detailed understanding of the subsurface conditions, again, as a basis for designing the foundation and understanding the seismic risks of liquefaction, which is the loss of strength of soil during seismic shaking. And as you can see, there's a steep slope toward the waterway. One of the other major concerns designing a facility like this for the geotechnical engineers is to understand, will those slopes be stable or not during seismic events. So this is a rendering or a photo of the facility site before it was developed. You can see there's a large warehouse building there, and parking and other infrastructure. The site has multiple use, a history of multiple uses. The latest was a warehouse building that had been there for quite a while, probably 40 or 50 years or longer, and was demolished to make room for this project. The next slide here is this was a rendering that was put together before the project actually began and took off, so that it could be shown to regulators and to the public and others, see what it would look like. A large tank like that is something that attracts people's attention, and PSE wanted to make sure that everybody understood what was going to be developed there. So, digging in a little further here, again, some slides from the reports that we put together. The way we approached this project was, and we'll get into it in a little more detail, is that we're in alluvial tide flat. There's very soft and loose compressible soils. They're susceptible to liquefaction, like I said, which means that they lose strength during seismic shaking and can cause excessive settlements, the type of settlements that could severely impact a facility like this, especially an 8 million gallon tank full of liquid natural gas. So we went through a lot of studies and did a lot of calculations and exercises to come up with what we call a ground improvement program. Instead of a deep foundation or a shallow foundation, what we've done is we improve the soils underneath the facility, and then we build sort of a conventional foundation on top of that. So we'll talk some more about the details here, but all these little blue dots are locations where we put in 36-inch diameter, 80 to 100 foot deep auger cast pile, which we call rigid inclusions, because they're not reinforced. They merely stitch the soil together, if you will, and mitigate the liquefaction and the settlement and the lateral spreading. So here's a kind of a cool graphic that the structural designers for the facility, Chicago Bridge and Iron, put together, and it shows all of the subsurface elements and then the 3D rendering of the facility itself. So you can see the tank, and then all those other pieces on the right are the actual liquefaction train, they call it, where and liquefaction, not to be confused with soil liquefaction, liquefaction of the gas. That's something that can get confusing, I guess. But the gas is brought in from the gas system that's in place in the pipelines that are have been brought to the facility, and then it's super chilled and stored in the tank. The upper left, you see a piece of infrastructure, and that's actually the pipeline that takes the LNG, the liquefied natural gas, and transfers it over to the waterway where it is it's used to fill the ship. So they have a special a pier and a loading arm that plugs into the ships, and they fill them up with natural gas, and that's how they get the fuel to move the goods. Here's a shot of the actual very beginning of the construction. The site's been cleared, the buildings are gone, and those two big rigs that you see there are, typically we call them auger cast rigs, but in this case, they were used to drill and install the ground improvements that were done for this project, the rigid inclusions. The methodology is really it's a hollow stem auger. So it has flights, and it screws into the ground, and it removes the soil in a 3-foot diameter hole down to 80 or 100 feet. And then grout is injected down through the auger, and as the auger is withdrawn, grout is placed in this annulus, in the space that the soil was removed. And that's how we construct the auger cast pile or rigid inclusions. Working on a site in one of the wettest winters in 2017 had some challenges. There was a lot of flooding and a lot of groundwater or stormwater that had to be controlled, and we'll talk a little bit more about that too. Construction isn't always neat and tidy. It looks good on paper, but when you get out there in the real world, you're probably going to get your feet and your boots and your pants and your jacket and everything else muddy and wet. So, one of the things that we did for this project was to do a test pile load program where we installed a series of these auger cast rigid inclusions, and then we constructed a reinforced concrete mat on top of it with crushed rock that replicates the foundations that were eventually built for this facility to support both the tank and all of the liquefaction equipment. So you can see a schematic here of that, and we constructed this. You can see the rebar mat here. A lot of steel and a lot of concrete that goes into a foundation like this to work together with the rigid inclusions below the surface and to support the equipment and the loads of the tank without allowing any settlement, both in a static and specifically during the seismic shaking condition. We constructed and tested this section of essentially foundation for the facility, and results were very encouraging under the design loads, about 6,000 pounds per square foot, static anyway. The settlement that was measured over an 8-hour period was only about 1/10 of an inch. So it was one of the ways that we validated the design. It's one thing to design something and say it's going to work. It's another to actually test it and see that it does. Part of the test program was to excavate down. I mean, we certainly couldn't excavate down 80 or 100 feet to see what the whole thing looked like, but we could excavate down 5 or 6 feet and see what the tops of the columns looked like. And again, it was very encouraging. Even after the load test, there was no damage to the columns. They were well formed and intact, and it was just one more piece of information that gave us confidence that we had designed this successfully. Another shot of the columns themselves as they're exposed. I mentioned that they don't have any reinforcement in them. There's no rebar that actually goes down into these columns. They merely, again, stitch the soil together and provide the improvement that's needed to support the foundation that's built on top. The rebar that you see sticking up there were actually part of the test program. Those were the reaction pile, the ones that the beam was attached to so that we could put the load on piles in between and successfully load the foundation, simulating the actual. Some of the other things that had to be done on the site, if you can imagine, we drilled for 2,000 36-inch diameter holes in the ground and filled them with grout. that extended 80 to 100 feet deep. So that meant that we generated a lot of spoils, excess material or material that came up out, during the augering. All of that material had to be contained and then sampled and tested for disposal or reuse on the site. Most of it got reused on the site, but it's a whole project unto itself just to manage the construction materials and the soils that come up out of the ground. The other thing that we ended up, or we didn't end up, we designed as part of this project was a stormwater management system. These ponds were constructed on site, and there's more discussion about this in the video, to contain all the groundwater. That slide I showed you earlier of the rainwater on the site and all that surface water, all that water had to be controlled and brought to these ponds on site. That whole 30-acre piece of property was bermed. Nothing left the site per our agreement with the Department of Ecology. And it was contained in these ponds, and it was allowed to settle, and it was checked, tested, and then discharged to the city's storm sewer for the permit with the city of Tacoma. Here's a nice slide. I just got last month, or earlier this month, just a few weeks ago, of the facility. It's complete. There's still a little bit of grading and cleaning up, and those storm ponds to the upper right there will be filled in. The permanent storm drainage system on the site will be activated. But as we speak, the gas is flowing to the facility, and it's being chilled and stored in the tank that you see in the upper part of the picture there. There's 8 million gallons of it. And then there's the pipeline that goes off to the left and across to the shoreline on the Blair waterway, where it's transferred to the ships for fueling. And I believe in about a month or so, they'll be ready to start fueling the ships, and they'll convert over from the fuel that you're using now, bunker fuel or diesel, to the LNG. All right, that's the end of the slideshow. I'm going to close that. And I have a video that our folks put together for this project. Get that up here. Okay, stop. All right. I don't know if I'm still sharing. One second. Find my. Apologies here. Trying to relaunch this so I can share the video. Here we go. Maybe. Well, I'm stuck here. Let me see. Megan, are you still there?
Yes.
So I'm having trouble getting back to the full screen on Zoom here so I can share this video. Clues.
Well, you're sharing your screen still, so I'm not, what do you mean you're?
Well, I wanted to make sure that I click the button to share the, maybe I need to stop sharing, but.
Yes, so stop, you can do the stop share and then.
Yeah, but I can't get my Zoom window open to see what I'm doing here. Minimized.
Try the escape button.
Nope. Hang on here. Close that. video. I'm gonna do that.
Can you do the stop sharing? Like,
I
can you hit
can't
the
find
stop
the
sharing?
button. It's minimized somewhere, and I don't know where it is.
It should be if you just like hover over your screen, it should pop up. Like
I know
stop.
it's not. Apologies.
Let's see if I can steal it from you, and then it'll like make you stop sharing.
Something happened. Here we go. We're
Okay.
back.
There we go.
Okay. Now let me launch. Okay. Now I'm going to share my screen. Screen 2. I'm going to share the sound and optimize share. Here now. All right. Here we go.
So my name is Jim Hogan. I'm the project manager for the Tacoma LNG project for Puget Sound Energy. The Tacoma LNG project is really serves two functions. Number one, it allows us to store natural gas in a liquid format for our customers so that we can reuse that gas in the wintertime when there's periods of peak demand. And that's called peak shaving. LNG or methane is the exact same natural gas that heats your homes. And methane is the cleanest burning fossil fuel. The second exciting part of the project is this is also a plant that will provide LNG as a transportation fuel for the marine industry initially, and hopefully also other heavy transportation industries. With changes in emissions regulations, we're seeing that many shipping companies around the world that operate large ocean-going vessels are converting over to methane as a fuel. LNG is the fuel of choice for ships that are converting to methane. In around 2011 or so, Hope Maritime Alaska came to us and asked us if we would be interested in being a supplier of LNG for their ships. And we'll have an 8 million gallon tank, and then we have the ability to produce 250,000 gallons per week of LNG. I started working with Dave Phelps and his team at GeoEngineers back in 2012. A big part of the role for GeoEngineers has been the geotechnical design of this facility, and we have just started our test piles for our ground improvement project here, which will involve the installation of about 2,500 auger cast in place piles.
I'm Dave Phelps with GeoEngineers. I'm a principal geotechnical engineer in charge for the Tacoma LNG project. GeoEngineers' role on this project really has been to define the seismic criteria for the site, to come up with a strategy for mitigating the seismic risks, which include liquefaction potential, lateral spreading, and to design a ground improvement program that will support the LNG facility that's being designed by Chicago Bridge and Iron. This is probably one of the largest projects I've ever worked on as far as scope, and we've involved dozens of people from GeoEngineers in all different aspects of this project, from doing the specific site investigation, drilling the borings, collecting samples, doing seismic shear wave velocity testing. We have taken that information and used it in our designs for the mitigation, the design of the ground improvement program. Our relationship with PSC has been really excellent. It always has been, and it remains. They've trusted us to work with them in the selection of the specific contractors and to write the specific specifications and put together plans working with the civil designers that meet the project needs. This is an alluvial tide flat with hundreds and hundreds of feet of very soft, very loose, potentially liquefiable soils that will shake and move during a seismic event. King Chin and the performance-based engineering group at GeoEngineers did all the detailed seismic modeling. Once we understood what the constraints were and how much movement we could tolerate, we then worked with PSC to come up with an acceptable ground improvement program that would support the facility and all the different pieces of it. That includes the 8 million gallon tank and then all of the process area. And we had to consider everything from the project site to the waterways beyond because of the potential for movement. And there's also a pipeline that goes from the tank across the peninsula to the adjacent waterway where the fuel will be transferred to the ships to fuel the ships. There are design seismic levels that are defined, and they're pretty stringent. They're a 2,475-year event that is a very rigorous event that's defined by the local geology, the Cascadia subduction zone, the Tacoma fault, the Seattle fault. All of those things are considered. The effects of that shaking are modeled specifically to this site so that we can understand during that earthquake, as the ground shakes and the pore water pressure increases and the strength decreases, what's going to happen. We looked at a number of options for providing, for mitigating liquefaction and lateral spreading. Conventional pile foundations were considered, but because the thickness of the liquefied soils are so deep here, a conventional pile foundation would never find any bearing. So basically we have to create a raft of ground improvement that does the job. We looked at stone columns, other techniques where we inject rock into the ground. Those were precluded because of an agreement with the Department of Ecology to not create preferential pathways for potential contamination movement. So what we ended up agreeing on were what we call rigid inclusions, or more commonly auger cast pile, which you can see going on behind us here. They auger down to 80 or 100 feet depth, depending on where we're at on the site, and then inject grout to create a 3-foot diameter grout column that's then cut off near the ground surface. A cap of clean crushed rock goes over that to create a bearing layer, and then on top of that, the foundation designers from CBI will construct the foundations for the tank and the process area. Those become almost a conventional spread footing type foundation, but it's on a very detailed and very extensive ground improvement program below so that all the performance criteria are met.
My name is Lucy Astorga, and I am a staff geotechnical engineer. My role here is to observe all the construction that's going on. We started a few days ago drilling our test piles. Well, it actually takes about 9 minutes to go in to drill about 100 feet. That's the ones we've been installing lately. And if everything goes well, about a half hour to be able to withdraw and fill the column with grout. And there's other demolition and excavation of ponds and removal of other contaminated things around the site.
As you can see, we are almost complete with demolition of all the buildings on the site. It's a 30-acre site, and we've had to take down about half a dozen buildings.
Other team members, Rick Moore and others, have been working on materials management, stormwater compliance. We've essentially contained all the stormwater on the site within a berm so that it's collected and managed. And we're also responsible for making sure that the water quality compliance requirements are met. And we have a very shallow groundwater table here. That's one of the challenges. It's about 5 feet below grade. During construction, all of the rainwater, any groundwater that we have to move for excavations is contained, tested, and then properly discharged in accordance with our permits with the city of Tacoma.
Geo has been a very integral part of our team. They've been with me the longest of all of our contractors and engineering firms on this project. Building this plant represents a least cost solution to our growing gas supply need. This plant gives, again, a level of assurance that on cold days like today, we'll have adequate gas supply to meet our customers' needs.
Okay. That's what I have. Happy to answer any questions. I can't see anybody, so I don't know who I'm talking to. But again, happy to answer questions, and maybe Megan can help me with that.
There's a couple questions in the Q&A. Did you see those?
I'm in the chat or the Q&A?
The Q&A.
Oh, Q&A. I didn't see that. Okay, here we go. First question, is natural gas the most effective fuel source of energy? How does natural gas compare to solar power or hydro power? It's a great question. Natural gas is still a fossil fuel. It's extracted from the earth and contained. It can be contained in different ways, but it is very effective as far as a fossil fuel goes, but it's not a renewable fuel source like solar or hydropower, something that solar power. I mean, I have solar power on my home, and hydropower is a wonderful source of energy, but every source of energy has potential drawbacks, environmental impacts, costs, pollution, things like that. So as we tried to explain in the video and in this presentation, natural gas is a better choice, if you will. It's not the perfect solution, but it's a better choice for fossil fuels. It's readily available, it's cleaner, it emits less emissions, and it's packageable in a form of LNG that it can be used for heavy equipment transfer, like those ships that are taking goods to Alaska. There's the next question. It was very fast on the video. Hope you can repeat, clarify. Is methane the cleanest fuel? Is LNG the same as methane? If not, how does it help ships transition from diesel to methane? I think that's I partially answered that the first question, but let me try to clarify here. Methane is natural gas. It's the same thing. It's just the technical term for natural gas. It's a very simple molecule. It burns very cleanly and very efficiently. LNG is merely taking the methane or natural gas and chilling it so that it's denser and more readily used and transferred to a ship where they can keep it in a special tank and then use it on board to move the ship to wherever they want it to go. So the difference is you can do the same thing with diesel or bunker fuel. You have a big tank of it and you burn it, but it's not as clean and it's not as efficient. And diesel emits more particulate matter and more CO2 into the atmosphere. That answered the question. Anything else? If it's not too big, I can put that video on the website and people can go back and look at it. You can also go to either GeoEngineers website and find the video. It's on our website, and Puget Sound Energy's website also has the video available, I believe. Or I believe they posted it on LinkedIn, on the Puget Sound Energy's LinkedIn page. They have, last I looked, they had a copy of the video available. I will try to upload it to this NEPRIS site so that it's available for people to look at again if they'd like to. Somebody already found it. Oh, there you are. I'm looking at two screens here. So there's the chat screen and a question and answer screen. Okay, so hopefully I've answered your questions. If there's anything else, please ask.
Someone asked, what is the risk if the fueling pipe to ships is ruptured?
Good question. So any rupture or release of LNG is problematic, obviously, but it acts differently than a liquid fuel like diesel or gasoline or something. The LNG will, if it's released into the environment uncontained, like a pipe break or a mishap when they're fueling, it will actually return to its gaseous state. So the risks and the problems are that, as it's regasifying and mixing with air, it reaches a point where it could be flammable if the air fuel ratio is correct, and so there's a risk of fire. There's also a risk of suffocation. You can't breathe methane. So those things are the risks if you were to spill LNG, and those things are very carefully thought out, and there are exclusion zones and fencing and containment and backup systems that help control that if it were to happen. There's also extensive fire systems if for some reason there were a fire on the facility. It's very, I think I mentioned some of the design criteria earlier in the presentation, that there are fire and spill release criteria that have to be met for a facility like this. the difference between LNG and say diesel fuel, if you spill diesel fuel, it floats on the water, it contaminates the environment, and to the extent that, you know, if birds or animals or people get coated with it, it can be very dangerous. The LNG, if it's, as long as you're a safe distance from it, will actually vaporize and go back into the atmosphere, and it's no longer a risk. Any other questions? There's another question here. We've seen systems designed for the worst case that encounter issues bigger than the worst case. Yes, Texas, Fukushima. I agree. That's part of being an engineer, is to do everything you can to mitigate risk to the public. You know, I am convinced that the design, the seismic design of this facility is as robust as it can be economically, and that it is a very safe facility. I didn't go into all the details, but the tank, you know, besides all of the ground improvement and the mitigation of liquefaction and lateral spreading that was done with the rigid inclusions, the tank itself is actually on base isolators. So the ground can move and the tank will absorb basically some of that movement. There's a lot of time and effort that's put into trying to make these facilities safe, but there's always a risk. And one of those risks is, you know, with time, we learn more about how to do a better job. You do the best you can with the tools you have. You always try to think ahead, but there are risks. But we also have to understand the rewards, and the rewards are that we have, you know, a cleaner source of energy, we have heat for our homes, we have fuel to move goods to people that need them. Those are the checks and balances of living in the world that we live in, of you know, designing and building infrastructure and living in cities and, you know, in the communities and the environments that we create and that we live in. Great question. I don't know if anybody on the call, in this group here is aware, but there was a lot of concern about this facility. There was quite a bit of there were some very concerned people who were opposed to the facility, and they were very vocal about it. And Puget Sound Energy and others spent a lot of time and effort trying to help those people understand what was being done and all of the measures that were taken to mitigate the risks. And you know, it's part of the risk and reward of building infrastructure to make our world the world that we live in. Anything else? Okay, it looks like we're done with questions. I thank you very much for the opportunity, and I hope you learned a little something. GeoEngineers website is certainly available for people to look at this project and others that we've done. And I hope that, I hope that it was informative, and encourage all of you to consider careers in science and engineering. It can be very rewarding to learn about the world that we work in and live in, and to contribute to you know, helping people out, helping people live better lives. I really believe in that.
Thank you. The chat and Q&A both have responded saying that it was informative and that it was a great presentation. So thank you so much for your time. And thank you for those who attended. This is recorded, so it will be on our site probably in about a week. So if you wanted to share it with others, you can do so.
Thank you, Megan.
Thank you.
All right. Take care, everyone.